Welcome back, folks, to another exciting JLAM Bio video. Today we are going to focus on thermodynamics and equilibrium. That's right, we can combine kind of units number, 7 and 6 and throw them together and make sense of it all. It's pretty exciting, but our focus today is actually going to be utilizing thermodynamic data to be able to determine equilibrium and even shifts in equilibrium utilizing Le Chatelier's principle. Super excited for this video today. We do not have a sponsor for this video. I've got my Big K Diet Cola soda open already. Fortunately, no ASMR for this, but very delicious. Let's go ahead and get started. So by the end of this video, you should be able to describe the relationship between free energy change and equilibrium constants, and then also calculate K from delta G. So again, do keep in mind that delta G tells us a lot about the spontaneity of a reaction. Remember that if delta G is positive, then the reaction is non-spontaneous, but if it is negative, it is spontaneous. So we need to kind of consider a reaction in terms of kinetics here. Now, if you remember, we talked a little bit about equilibrium and that we kind of lied to you in Chem 1, because remember when we told you that if you take 2 moles of, let's say, methanol and we mix that with 3 moles of oxygen, that we're going to get all 2 moles of carbon dioxide and 4 moles of H2O. Now, based off of equilibrium, we know that that is not the case, that most of these types of reactions have that double arrow in there. So you have to keep in mind, do we get all product with this? And the answer is no, we don't get all product. It all depends on where equilibrium lies. It all depends on that value for equilibrium, which we know as K, our equilibrium constant. So at equilibrium, we do want to keep in mind that reactions have the lowest value of free energy. So in this particular instance, equilibrium is going to occur right here. We have the lowest amount of energy. If we have 100% reactants, we don't have the lowest amount of energy because there is still the capability to produce some products, and same thing with 100% of products. Now, again, where this point here lies is going to depend on what the equilibrium value is, whether it's greater than 1, whether it's less than 1, etc. But because we want to have the lowest value of free energy, that means that delta G is going to be 0. All right? So if we think about delta G as being equal to 0, and we remember our formula is that delta G of our products minus G of our reactants. So if delta G is equal to 0, that means that the Gibbs free energy of our products is equal to that of our reactants. Okay, so we can kind of think a little bit about that in terms of equilibrium and knowing delta G and being able to determine which way the reaction is going to go based off of Gibbs free energy. So it's really important for us to remember the relationship between Q and K when we talk about thermodynamic equilibrium, because again, our relationship between where we are in terms of the amount of reactants and products at any given time needs to be related to the material at equilibrium, what our concentrations are, our pressures are, etc. So we need to remember when we have Q is greater than K, that's going to favor our reactants, and when Q is less than K, that it's going to favor our products. Okay, so those are some important things to keep in mind. We want to be able to establish a relationship between the equilibrium constant and thermodynamic information given in delta G. Okay, so if we kind of think about this reaction graph here, which we talked about before, and we're going to consider the Haber process here. Remember the Haber process, we're going to take nitrogen and we're going to add 3 hydrogen to it, and that's going to produce 2 ammonia molecules. All right, so if we're trying to figure out Q from this, right, remember we figure out Q the same way we look at K. We're going to look at the concentration of our product over the concentration of our reactants, multiplied together there. Now let's imagine that we're at this spot right here. Okay, now that spot we have all reactants and no products, right? So if we have all reactants and no products, that means that this number down here is going to be relatively big, right? Because again, we have all reactants and no products means that this is about 0. So that tells you that Q is very, very small. And that makes sense, right? Because if Q is really, really small, then the reaction is going to proceed towards your products. It's the same concept if we look at Q over at this point. If we look at Q here, right, the number on top is going to be really big, and the number down here is going to be really small. A big number on top of a small number is going to give us a really, really large Q. So here, Q is going to be much greater than K, so equilibrium is going to shift back to the left. Okay. The only instance that we get here is that Q is equal to K, which results in no shift in the reaction. Okay. Just kind of a rehash of equilibrium here as we think about this process. So the reality is it's actually quite easy to connect Gibbs free energy and the value for K. And this is the equation that we're going to use here. So we have delta G and we have K in this. We kind of like to call this the rat link expression here because we have negative RT and then the natural log of K. R here, be careful. It's not the normal R value that we've used for ideal gas law. It's still one that can be used for it, but here it's going to be 8.3154, which I think is the one that's used for pascals or kilopascals or something like that. But that's the R value we're going to use here because we can use joules as a part of that. Okay, our temperature is in K, and then K is the equilibrium constant here. So if we think about it, and we plug in a number for K, right? And K is greater than 1, if we take the natural log of that, that number is going to be positive, okay? And if K is positive in this expression, notice we've got a little negative sign here, so delta G is going to be negative, right? And if delta G is negative, then the reaction spontaneously goes from reactants to products, okay? So this favors product. Right? Because the reaction is spontaneous. If K is 1, right? Well, then the natural log of that is 0. So delta G is 0. So we must be at equilibrium. And if K is less than the value of 1, then ln of K is negative, which makes delta G positive. And we know if delta G is positive, it's non-spontaneous, okay? Which actually means that favors our reactants. So I can't even get any writing on here, okay? So do kind of keep these things in mind in terms of whether it's favoring reactants or products. It's easy to determine G based on the sign of K. All right, let's do a practice problem. The overall reaction of the rusting of iron by oxygen is given by this particular equation. Using the following data, determine the equilibrium constant for this reaction at 25 degrees Celsius. Okay, so a couple different things that we're going to have to do here. The first thing we need to do is we need to figure out what we're solving for. So we're solving for K here. In order to know K, I need to know T, R, and delta G. Well, I know this value, and I know that value. Okay, because we have a temperature here, R value, 8.31. And so therefore my delta G value, I can actually calculate from the information listed here. Okay, now because R is in a unit here for joules, we're then going to want to get delta H into joules as well, because when we're solving for delta G here, we want it to be joules so that it can plug into our equation. Okay, so let's get delta H first, or the delta H is our products minus our reactants. So we have our product there. So we're going to have 2 times negative 826. We're going to subtract 0 from that. So we get our delta H, okay, which is 1,652 kilojoules. Or if we get into joules, that is going to be 1.652 times 10 to the 6th joules. We do the same thing to calculate delta S. Delta S, we have 2 times 90 minus 4 times 27 plus 3 times 205. That's going to give us a value of negative 543 joules. So now that I know delta H and delta S, I can plug that into my expression. The delta G equals delta H minus T delta S. So I can just plug those numbers in. So delta G equals 1.652 times 10 to the 6th minus, remember T is in Kelvin, so 298 times negative 543. Plug all that in and get our delta G value. I mean negative 1.49 times 10 to the 6th joules. It's our Gibbs free energy. Okay. I do apologize earlier. There should be a negative sign on this first one here. Okay. So I did leave that out, but I do apologize. So now we're able to plug that into our expression. We have delta G. We plug that in here and we solve for K. What's really nice is that we can actually figure this out pretty easily. If we rearrange this equation here, what we end up getting is that delta G over R times T equals the ln of K. And in order to get rid of ln, we use the E. So our K is equal to E times delta G over RT. Now what you're going to find here is if you plug all these numbers in, is that K is actually going to equal E to the 601 power, which is going to give you an overflow in your calculator. But that actually tells you that K is really, really large. Okay. And if we know that K is much greater than 1, then we know that the products are favored in this reaction. Okay. Let's move on. Something else that we can also do with this is we can actually calculate delta G for reactions that are not at equilibrium as well. And for this, we actually use a very, very similar formula. The only key differences here is that we have delta G equals delta G at standard conditions plus RT ln Q. We're using Q instead of K because remember, we're not at equilibrium. So Q is the reaction quotient. Remember, we calculate that. We find that the same way we do K. The only difference is that Q is not at equilibrium. Same gas constant here. It's going to give you the free energy at standard conditions, or it may ask you to calculate them. And then we can determine delta G that's not at standard conditions. Based on that information, we can then predict which way the reaction is going to shift. So consider the reaction here where delta G is negative 6.0 times 10 to the third. Predict the direction of the reaction will shift to reach equilibrium. So here, again, we're given our delta G. We want to predict the reaction is going to shift, so we need to know what our delta G is. This is delta G 0, by the way. So we're just going to go ahead and plug this in. So to our previous formula, so it's going to be negative 6 times 10 to the third. Okay. We're going to add that to R, 8.31, times T, 298. And then we're going to plug that in for Q. Remember that Q, same way we find K. So it's concentration of N2O4, or partial pressure, depending on what we're looking at here, divided by NO squared. Okay, so we're going to plug that in here. So we're going to get the natural log of 0.50 times 0.21 squared. Plug all those numbers in. What you find is that delta G is 0. And which way is the reaction going to shift? Well, since delta G is 0, we mentioned that before, this is already at equilibrium. So we're good there. All right, we're going to do the same thing for part B. Pretty much the exact same type of problem. We're just going to plug in 8.31 for our R value, 298. And the same thing, natural log. We're going to do a little bit different numbers this time. So 0.29 squared. And what we end up here with is delta G is equal to 1 times 10 to the third joules. Okay. And so predicting which way the reaction shifts is actually not that difficult here, because if we remember our formula, delta G equal to the delta G of our, or total G of our products, sorry, sum of our products minus sum of our reactants. Well, think about what is the only way that we're going to get a positive delta G out of this? Well, if that's the case here, we know that our product's delta G has to be higher than that of our reactants, right? If our product's delta G is higher than our reactants, again, equilibrium shifts to where delta G is 0. So that means that, again, if products are higher than our reactants, that means that this reaction is going to shift towards the reactants. We have too much G in our products, so we need to shift some of that over to our reactants. Okay. Again, it's just plugging in, being able to solve for these expressions. We'll do some practice problems with this and move on in just a little bit. All right, guys, hopefully pretty painless today in terms of being able to go through and complete all the stuff that we need to complete for today. Hopefully you'll be able to describe the relationship between free energy change and equilibrium constants and calculate K from delta G, just like we did in some practice problems. Hope you guys have a great day. We got one more video of this unit, and we will talk to you later. Have a great day, guys. Bye-bye.